Okay, so this tutorial is going to be on rotation, and more specifically rotation control. Uh, but it's come to my realization I never made a tutorial on how to do, you know, how to model a 3D thing that can spin. And so this isn't, it's going to be made within the KV modeling folder, but it's odds are I'm going to put this as like another MATLAB tutorial rather than, you know, a KV tutorial. So, without further ado, let's get started. So, first of all, we have our main file that we're going to run. We're going to call it rotation control. This is the only file that we're actually going to be running. Right, there we go. And just per normal, we have our start, we have our stop, and then we also have to define, like time span, right? dt is equal to 1e negative 2, and t is equal to 0 dt, and let's just do 25 seconds, and you'll see why this one's a bit longer. We're going to be doing our things in Quaternions, so if you're unfamiliar with Quaternions, I would highly recommend getting a little bit more familiar with them. There's plenty of resources on the internet for getting used to them. In terms of this project specifically, I'll be following this, this research paper. It's a little old, but it has all the ideas that we need, including equations of motion, as well as a basic a controller for this type of system. And you can see they go into the math quite a bit, as well as a good explanation. So I would highly recommend this paper. You can literally just search up the title, and I think, it's been released for public use now. Um, but yeah, so this is what we're going to implement. Um, so yeah, so let me just pull up my thing. Okay, so quaternions are just a fancy way of representing rotations, and I'm not gonna lie, I still have a little bit of difficulty, understanding them. That being said, I think Euler angles are something that anyone can understand, and so the first thing we need to do is come up with a scheme for going between Euler angles and quaternions. And whoops, wrong thing. And this video is going to be a little bit more, raw than my normal videos, in that you'll see me, actually going through everything, pulling up references and they're related. So yeah, uh, let's just do this. Let's just search up on. I'm searching it up on my other screen. So Euler angle to quaternion conversion, and well, let me just pull it up here. So yeah, it's the first thing, quaternion to Euler angles. So these are the ways to go from quaternions to Euler angles. Let's see if we can find one that goes the other way. Here we go. So we can see that this is the methodology chosen. Oh, sorry, it's right here. This is the raw formula, you could say. And so this is going to sound kind of crazy. We're just going to implement this in straight, right? There's no reason to, to shy away. So let's create a new function. Oh, not live script. Remove that. A new script. We're going to call this E to Q, standing from Euler angles to quaternion. It's just going to be a quick conversion thing. And so we want to feed it in a bunch of Euler angles, and we want to get out a bunch of quaternions. So keep in mind, we may not necessarily want to do them one by one. We may want to do them, all at the same time. So let's just do that. E to Q, and I'll just comment it. Convert Euler angles to quaternions. And I'll just keep the format here, which is going to be that, the first one we're going to expect it to be yaw. The second one we're going to expect it to be pitch, and the last one we're going to expect it to be roll. And we're going to follow the convention of the what's it called? The convention followed here, which I believe, if I'm not mistaken, the first value is the one that is the scalar. Yes. So in this quaternion, the cosine term here is the one that's going to stay a scalar, and Q1, 2, and 3 are going to be the vector part. If you're unfamiliar with how quaternions work, there's plenty of books on the internet that can guide you. So let me just leave another comment here. So, whoops, Euler angle format, and then Quaternion format. So for Quaternion format, Q1 is going to be the scalar part, and then Q2 to 4 is going to be the vector part. And we just want to make sure that anyone who reads our code can understand this, ASAP. So the first thing we have to do is figure out, how big is the input, right? E could be something that's, very small. It could be something that's very large. So we want to get the size of E, and we're expecting E to be a row vector, right? We're expecting E to be a column vector, where in one row represents one specific instant in time, and then column 1 represents yaw, column 2 represents pitch, and column 3 represents roll. So the rows are going to be irrelevant, and instead we care about the columns. No, wait, that's a mistake. Actually, no, we care about both of them. Let's just do this. Rows, comma, cols. I forgot my matrix. Okay. So this will give us the rows and columns. And then we want to convert our quaternions, we want to initialize our quaternion as zeros. And we want to have the same number of rows. But because of the way quaternions work, we're going to have 4 rows. Or four columns, my bad. So for every Euler angle in a row, for all the Euler angles in a row, we want to have an equal quaternion in the row. The size of the columns of the Euler angles will be 3, right? Because we have 3 Euler angles for one orientation. For quaternions, are going to be 4. That's it. Then we, then we just go through everything. So for I is equal to 1 to rows, right? So we want to iterate through every row. What we're going to do is we're going to say Q for that row is going to be equal to, I may have to go down one more. Okay. Let me just hide this. Yeah. And then we just, we follow the format exactly, right? We have our cosine of, let me pull this thing up one more time. This lovely thing. Now, you can type this out if you want. I do not have the mental patience for this. Rather, this video is going to be way too long if I try to do something like that. So I already have it done on another document. I am just going to copy paste this in. Now, something you may have noticed is that the 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Something you may have noticed is that this is going to return it to us as a column, right? We don't necessarily want that. We want it to be a bunch of rows. So we're just going to add in a bunch of dots here, so we don't have to, deal with that later. And this should be good. We don't really need this columns here, but if we wanted to make sure, we would put an if statement here to make sure that there are in fact 3 Euler angles for every instant in time. But we don't need to worry about that detail right now. We'll just write our code, as if we're the only ones using it. So yeah, so we have our Euler angles to quaternion converter. So what do? Well, we have our E naught. Let's just quickly test it. E to Q, and we're going to put in E naught. And then let's just display Q naught. And let's just run this rotation control. Okay, and this makes sense, right? We have our Euler angle set to 0. Our quaternion should, input should give us more or less a 0 value, right? And what this is saying is that we're going to rotate any number about no axes, which is to say that 0 for our Euler angles corresponds to 0 for our quaternions, right? For those of you who understand how quaternions work, that sentence made sense. For those of you who don't, I would highly recommend reading into it a bit more. So we have our quaternions. Let's just set up our initial angular velocity as well. And we'll just say that our initial angular velocity is just going to be 1 in the x direction, 0 in the y direction, 0 in the z direction, or about those axes. And so we have that, and let's just set our state 0 is equal to q naught, comma, w naught. So the first So our state vector has 7 variables now. 4 variables are going to be the quaternions, and then the other 3 are going to be our angular velocities. And you'll see a bit later why I chose to do it like this. Another thing we're going to do is, actually no, let's just try and implement our rotation stuff right now. Yeah, we're not gonna do anything else. Something else that we have to define is vertices, right? We're gonna be making a shape basically in MATLAB, and so we need to do some, we need to account for vertices and edges, right? This is what we're gonna use to define, say like a block. You can check for yourself, but these are the values that would make up a cube, right? These are the 8 corners of a cube, and then correspondingly, we can define the faces, not edges, faces, as these values. I am not going to go into the details here because it is not worth it, but you can confirm for yourself that, if you go between these 4 points, these 4, these 4, these 4, these 4, and these 4, you'll get the 6 faces of a cube. And then one more thing we're going to do is just add in something for color. So color is equal to, and it's going to be an RGB matrix, so we'll just do 0, 0.5, and 0. The scale is 0 to 1, not 0 to 255, just so you know. Once we have this, we also want to define our inertia matrix. So the inertia matrix, we're going to be defining it as a diagonal matrix, and it's going to be, we're going to assume all 3 axes just have a, we're just going to assume we have principal axes of 1 for now, nothing too special. And now we need to figure out how to put all of these in and make like an actual, block, you could say. And so for that, we're going to go to our class function. We're going to define a class called block. And this is where I have to start referencing my thing because I don't remember all the details yet. But it's going to be a handle block, or sorry, a handle class, because we're constantly going to be changing our values. And let's just define its properties. So we have our state initial, we have our state simulated, we have our dynamics. We are also going to have our t-span and our dt. Just dt. And for the visualization part, we're going to have our vertices, faces, and color. Oops, I almost forgot our inertia here. Right, and these are the things related to the simulation. These are the things related for actually drawing it out. So let's just do that. So we have state 0, state simulated. Sorry, no, state simulated is not an input. We're going to put in our dynamics. We're going to put in our t. Actually, we don't really need to put in our dynamics. We're going to define our dynamics as part of the class itself. So we have our state 0. We have our t-span. We have our dt. We also need to put in our vertices, faces, color. How could I forget inertia again? And there we have it. Those are the things here. I'm gonna be speed running through this, so I'm not gonna try and comment everything right now. But if you're writing this for yourself, definitely leave comments for the stuff that you think deserves to be remembered. Equals dt obj dot vertices equals vertices, obj dot faces equals faces, obj dot color equals color. And one more thing that I want to put down here is this. I'm going to put a function in here. It's going to be called obj.draw. And you might be a little confused as to what this is right now, but we're going to define this. We're going to define this right here. And what this draw function is going to do is we're going to feed it the object itself, and it's going to draw the object, right? It's going to create a plot and draw it for us. So let's see, how would we do such a thing? Well, I almost forgot the h up here. So this is the h, which is our handle, and you're going to see why this comes in handy and why I remembered it for this case specifically. So to draw an object, we can use what is called the patch function. And what the patch function does is you can feed it a bunch of faces and vertices as well as a color, and it will fill in everything in between and draw like a physical shape out of that. So what we do is we say that we're referencing the object itself, right? We're referencing the object's handle, and we're going to say that it's going to be equal to the patch function. And for the faces value, we're going to feed it obj.faces. For the vertices, we're going to feed it obj.vertices. And then I'll just go to the next line. For face color, we're going to do obj.color. Whoops. And then we're just going to do, oh, whoops, I didn't do that. We're going to just do some other stuff. So we're going to set the view to be 45 degrees from the bottom, right? So it's going to have an elevation angle of 40 degrees and then azimuth angle of 20, or the other way around. Whichever one, we're going to get a nice diagonal view. We're also going to do axes equal. This will just set all of our axes to be equal. We're going to do a grid on, and we're going to do a rotate 3D on. And you'll see why these come in handy later. So grid on, just, we'll see a grid, and rotate 3D means we can interact with it to, rotate about it. And believe it or not, this is actually enough, you could say, to, actually draw a cube. So just quickly go into rotation control and run it. Oh, yeah, my bad. I forgot to create the block itself. So let's just go up here. We're going to go into object. We're going to copy that line down here. And we're going to call this block, except it's going to be in all caps. Color we've defined, faces we've defined, vertices we've defined, dt time t-span. Have we defined t-span? No, we defined it as t. Let's just add that in, t-span. Alright, so we have our t-span, inertia, state 0. Yeah. Okay, so let's just run this one more time. And it should create a block somewhere around in here when it's done loading. Let's see what the holdup is. Okay, there we go. And you can see we can draw. We already drew a box. Right? Pretty nice stuff. We can't really rotate because it's kind of fixed right up. There we go. We can rotate. It's just a bit slow. All right. Yeah, my apologies. It was the azimuth angle was 45, and then the elevation angle was 20. But yeah, you can see that we have a cube and we can rotate about it, right? Now we have to get into the more interesting things, which would be how to actually set up the the rotation stuff. So let's go back into our block and let's define a new function, which is going to be our dynamics function. So we want to spit out a dx value, and we're going to call this dynamics. And as per our RK4 value, our RK4, or sorry, yeah, as we've defined our RK4, this is how we want to set up our function. So we'll go back into the block. We're going to close the Euler angles thing for now. So this is how we're going to be defining our function. Is we're going to feed it the time. Yes. So we're going to first feed it the time. Remember that we have to feed it object first. So we're going to feed it the time. We set the object, the time, the state, and then whatever else we need to feed it. So in this case, we're going to need to be feeding. We need to be feeding it inertia, and then I think that's all for now. Just inertia. Yeah, just inertia. I'll just leave a comment here so it doesn't get in the way. Oops, there we go. And then we'll just define the end of our function, press enter, go down again. Okay. Now, what exactly do the dynamics look like? Well, this is a bit of a complicated topic. I will not lie to you at all. But basically, we remember that we have our quaternions as the first 4 variables, and then our angular velocities as the next 4. And then we don't have any control torques right now, so this is just going to be a free rigid body rotation. If we go back to our paper, let me pull this up. We can see that they've defined, what the dq values are. They've defined them right here, right? So these are the, the rotational dynamics in quaternion form. These are the equations right here. So we just have to figure out how to implement this. Let me zoom in a little. Okay, so we can see that to get the change in our quaternion variable, we just do -1/2, add a 0 to our matrix here, and then we just multiply it with our quaternion. But this is a quaternion product. This isn't a normal product. Let me go up here and define. Let's see if they've defined it, which I'm pretty sure they have. There it is. So this is what the quaternion product is. This looks like a nightmare. Once again, we're just going to copy this in. There's no need to, sit around trying to like work out all these little details ourselves. So let's just do that. Yeah, we're just going to create a new script. We're going to call this QP, which is going to be standing for quaternion product. It's going to be a function, and our output's going to be the quaternion product, and our input is going to be quaternion 1 and 2, Q and P, and it's going to spit out QP, which would be Q and then the Kronecker the symbol, and then P. And let's just define this. Once again, I'm sorry for not sitting here and slogging through everything one by one, but I'm just going to copy paste my old code, which I am certain works because I know I will make a typo in here. A good way to remember this is that for each row, it just goes down 1, 2, 3, 4, and then it goes across Q1, 2, 3, 4, Q1, or Q2, 1, 4, 3. Or sorry, no. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. There's a pattern here. I don't think it's particularly required to remember it. Whoops, I defined this wrong. Q and then P, and we'll just call this, actually no, QP is here. Okay, because of the way I've defined it in the other one, I have to change it around a little. I guess I'll have to rename my function as well. QP, or no, PQ, 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 PQ. Okay, and I'll just rename this. Nope, I didn't mean to do that. Give me a second, let me grab that file again. Where'd it go? There it is. Restore. Okay. We just want to rename it to be PQ. Enter. Now let's close it. Okay. Just gonna copy paste this. No. Open this. There we go. Everything is in PQ form now. Okay. Yeah, sorry about that. A little bit of a misclick. Okay, so yeah, we have our PQ, which is going to be our quaternion product. And now let's just look into implementing it. So we have our block in our thing. Let's just define it. So we have our DQ, which is going to be equal to negative PQ, and the first thing we're going to feed it is 0, comma W. And the next thing we're going to feed it is Q, right? This is the Kronecker product we're doing. And then all this is going to get divided by 2, right? We're just going to put that in at the end. We also have our DW. So our DW is defined right below it. Where'd it go? Right here. And this looks pretty complicated. There's a way to make our lives easier, which is we basically factor this thing out. We factor out this inertia part. So yeah, what we can do is we can factor this out and move this to the end, and yeah, that's how we do it. We also have to define a little bit of a cross product thing here, but we can just copy paste the function from last time. So yeah, let's just do that. So first thing we have to do is copy paste the function from last time, the Cartesian cross product. So Control C, Control V. Now we have our Cartesian cross product here. Obviously not the most efficient, but it's enough for what we need it to do. Looking at our function, we can do a left divide by I. So we're going to call this I, and we're going to call this X, just because it makes my life easier. And since we're doing a left division by the MATLAB has a nice function where you can just put in a slash like this, and MATLAB will know that it's a left division. We have -1 times Cartesian cross product of, what was it, of W, I, and then we want to multiply that by W. Let's just check on our thing. Okay, no. So we're feeding it W, and then ICM, times w. So this is wrong. We're going to do times w here. And then within our function here, so it's -1, this cross product, and we have to add in a torque here. There is no torque right now, so we just leave this blank, but you can see, you'll see once we go further down the line, we'll have to add in our own torque. If there's going to be any errors, it's going to be right here because errors here. Because I forgot to like transpose one of them, but we'll see if that's a problem later. So we have dx, and this is going to be equal to dq, dq, comma, dw. And that's our change. That's our dynamics function for now. And so, yeah, that's pretty straightforward. And then let's just add in our, simulate function as well. So to simulate something, what do? We just have to go down. We'll just make a new function for it. So function, it outputs nothing. It's going to be simulate, and the input's going to be object. This is pretty straightforward. So Q is just going to be, state S is going to be zeros, and it's going to be the length of obj.tspan, and then this one's going to be length obj.state I, or did we define it as state I or state 0? State 0. My apologies. State 0. Alright, so we have our state S right now. Oh, whoops. We're actually referring it to object.state S, not just state S. And then, yeah, let's just go through this. So for A is equal to 1 to length obj.tspan minus 1. We want to apply our, I think so, obj state S, A plus 1, comma, everything. It's going to be equal to RK4, and it's going to be at obj dot dynamics, and per usual, our inputs are, the way we've defined them in the RK4 function. So t dt state, t dt state. So obj dot tspan a, obj dot dt, obj dot state s a. Something I forgot to define up here is we have to do obj dot state s first row, all columns. It's going to be equal to obj dot state 0. I almost forgot to define that. We have fed it state s. What else do we need to feed our dynamics function? We also have to feed it the inertia. So let's just do that. Obj dot inertia. And this should be good, I think. The last thing we have to do is figure out how to animate it. So there's going to be another one of those functions which you guys are not going to like, because I'm just going to, from your perspective, I'm just copying them from what I had before. But I assure you, these things are very annoying. You don't want to be sitting here writing it out every time. Let me just pull up my rotation control. Okay. So to simulate this thing, we just what we're basically going to be doing is we're just going to be going through everything. Sorry, did I write? Okay, no, I wrote animate. Okay, so to animate this thing, all we have to do is go through all of our stuff one by one, all of our data points, right? And every time we do, we just have to redraw the figure, or update the figure, you could say. So we're going to set, okay, so the input's just going to be the object, and we're just going to set some limits first. So because we're dealing with a 1 by 1 by 1 cube, we're going to set the limits of our figure to be -2 to 2 in all three directions. So we have x lim, y lim, z lim. Then we have to do view 45 comma 20. And then we just do for I is equal to 1 to length obj.tspan. So go through all of our tspan. And what we want to do is we want to get a rotation matrix, which, okay, we haven't defined it yet, but we're going to define that right now. So what a rotation matrix is this is just how MATLAB is best at, applying or being able to apply rotations. And the way we do that is we convert from quaternions to an attitude file. So it's going to be a Q to A. This is just another function. It's just you go to Google, you search it up, it'll give you some nightmarish thing that looks like this. Even I don't have the patience to be sitting here typing all this out. I found someone who put this on the internet on their GitHub, and I'm going to be using it as well. Thank you to Andrew, though. So anyway, we just copy this whole thing and shove it in here. It's going to spit out an A file, shift enter. Okay. Basically, the first line just makes sure that it's it's in the form that we care about, and the second line just converts it into like a rotation matrix, right? So this is the first value of the rotation matrix, second value, third value, and it's a 3x3 matrix. That's what a rotation matrix is. Anyway, we have our Q to A function defined. The next thing we have to do, so yeah, let's just apply this. So our rotation matrix is going to be Q to A, and we feed it obj.q. Sorry, no, obj.state s. We feed it the first 4 values, and we feed it only for the for the ith row. We're feeding it columns 1 to 4. Yeah. And that'll create our rotation matrix. Next, we have to update the attitude. So for this, we're going to create a new function down here. This is just going to be an update attitude function. So function, and this is going to be no output. It's just going to be update attitude. And the input's going to be the object itself plus a rotation matrix. So MATLAB is great in that, it's very easy to update, or the update attitude, or update the vertices, right? We've defined them up here, we defined them in our old script as, these are our vertices. But then to actually apply the rotation, all we have to do is multiply the rotation matrix by all of the vertices. And MATLAB makes our lives very easy here. And the way we do this is we say v new is going to be equal to, and this is going to be, alright, it's going to look, there's probably going to be errors here, and you'll see why very quickly. But we're going to multiply our vertices as column, as a column, or sorry, as a row vector, and then we're going to convert it back into a row. I think this is what I wrote last time. I'm hoping it's right. I know it worked at some point. It's been a while. I may have to go back and review it, and you'll see me do that if we get there, when we get there. Anyway, we define our new matrices as by multiplying the rotation matrix by our old vertices. We just had to convert it into a form that I can understand, convert it back into what we had before, and then apply that same rotation and apply that to our object. And so this will update the vertices that represent our object. Once we've updated our attitude, actually, let me just do that. Obj dot update attitude, and the input to that is just a rotation matrix. Yeah. Now we're just gonna set a title of our thing. This is just to make diagnosing problems easier. And the title is just going to be obj.tspan I, and maybe we want to just have %.2f. So this will just tell us what so the title of our graph is just going to be like our current time value, and it's going to have 2 decimals, right? Because we're doing 2e to the negative 2. So yeah, let's just run a quick test. It's probably going to be errors. Oh no, there were no errors. It actually ran. Oh, that's because we didn't set, okay, yeah, we didn't. So we've created the block. Now we have to do block.simulate. Let's see if there's errors here. Okay. So let's see what the error is and slowly diagnose the problem. Index exceeds the number of array elements in block dynamics. So let's go up here to block dynamics and see what the cause of this error is. T, X, I. How does our dynamics function expect the input? Well, you know what? We're not going to bother. We're just going to use our trusted method. Display obj. This video is going to be a lot longer than normal, so if you want to skip around, just skip like, I don't know, 2 minutes at a time until you see that I've overcome my problems. If not, then good job for sticking around. I don't know why you would do that, but if you choose to do it, then congratulations, I guess. Actually, wait. We can see the inputs right here. Okay, so for some reason, it's feeding in. Okay, so our DT's value is right, but our state value is wrong. Okay, wait. So, okay, let's see. Where exactly did we go wrong? Our dynamics are what they should be. Our time is 0. Our DT is 0. The next value should be our state vector, but for some reason it's 1. I think this is grabbing the index. X and 0. Okay, I may have to cut this out while I diagnose this issue. But why is it only feeding in one value? Let's see here. Alright, what are we displaying in here? X and 0. T, dt, x naught. Go into block. Oh, okay. It's only displaying the first row. We want to feed it everything in the first row, not just the first value. Okay, that's good. New errors. Incorrect using this. Ensure that the number of matrices in here. Error in block dynamics. Okay, so in block dynamics we have an error. The error is in here somewhere. So we have to ensure that I and omega. Okay, so let's just do this. Display omega. Let's see what this should. We should expect it to be a column actually. Okay, that's our error. So basically, I is a 3 by 3 matrix. Omega is currently a 1 by 3. We want it to be a 3 by 1. We just add in a thing here, and that should fix that error. Okay, new error? I hope so. Error using this. Dimensions must agree. Okay, yeah, once again, this whole thing is currently, here, you know what, I'll show you the errors one by one. But if we display, and then this whole thing, we'll see that this is also going to come out to be a row instead of a column. Yeah, it came out to be a row instead of a column. And so what we have to do is we have to add in, we have to transpose it basically. So to do that, we just add in another thing. Now we try it. Oh, what does this give us? Array, dimensions of arrays being concatenated are not consistent. Okay. Yeah, you can see why this is very annoying to do. But this is debugging. So odds are that one of these is going to be a vertical thing and the other one's going to be a horizontal thing. That's probably why it's being like this. So let's just display both of them and see what this comes out to be. Okay, yeah, they're both vertical. We want them to be horizontal, right? The way we've been defining our whole system is we want every row to be a different time step. And if we do this, boom, it works. Okay, now let's just get rid of this so our code doesn't run very... I didn't mean to get rid of those two. I meant to get rid of these two. And let's just clear CLC and run rotation control. No, I forgot to get rid of this in here. You know what? I'm not going to get rid of this. I'm just going to keep it. I'm just going to comment it out because I think this is a very helpful thing to have ready. Okay, so we simulated our thing and now we just need to animate it. To animate it, let's just go back in here. It's called block.animate, I believe. Yeah, and we're not feeding it anything special. So block.animate, let's just add that down here. Block.animate, and let's just run it again. And hopefully there's no errors. Is it animating? You know, it might be smart to give it some actual rotation. Actually, wait, does it have rotation? Did I just miss it? Block.animate. Why did that not work? Oh, I know why. Okay, so within our animate function, when we go through this, we actually need to give it, we actually need to tell it to update the drawing. And we do that by passing this thing called draw now, which basically says whatever figures you have up, just redraw them right now. And we're also going to add in a pause function just because that did not feel like it was 25 seconds long. So if we do this now, there we go. And we can see it's spinning about, it's spinning about in a direction. Whether or not it's the right direction is a different story, but you can see it is spinning. Yeah, it's doing its job, barely. And it will continue doing this until, the animation time is finished. But you can see that this is the basics of, how to draw. Actually, I'm pretty sure it's drawing in the wrong axes. Because we set it to rotate in the Y. Did we set it to rotate in the Z axis, or was it the X axis? Well, it's a debugging issue, regardless of what we say. But yeah. So this is the basics of how to make things rotate. Very pretty. I will get into the. Unfortunately, this video is already way too long. Yeah, it's already 40 minutes. If not if, but for later on in a little bit of time, I'll look into fixing this error of why it's rotating about the x-axis instead of the z-axis. But yeah, these are the basics of how to do rotation control. I'll figure this out. I'll post a correction video either today, tomorrow, or the day after. And yeah, good luck. If you figure out the error, leave it in the comments. All right, goodbye.